some physical properties of liquids. So the first thing I want to talk about is surface tension. So here I have a picture of a water strider. So you might have, if you've ever been to like a pond or something, you might have seen these little bugs. So they like kind of flit across the water and they don't float. So they take advantage of what's called surface tension. So basically, imagine you have a cup of water. So if you pick a molecule in the middle of the cup of water, it's attracted on all sides to the other water molecules in the cup, right? But on the surface of the water, you have these water molecules with nothing above them except for air. So, and the water molecules are not going to be attracted to air. So they're only attracted to their neighbors around them and below them, okay? So this means that to compensate for this, they have to attract their neighbors really hard, more so than usual. So this results in what's called surface tension. So it's somewhat hard to break the surface of water. So, and the water strider takes advantage of this. It has a very light weight. So you can see the depression in the water that's made, and the water holds its form. So that's called surface tension. So if you want to see this in action at home, what you can do is you can take a tissue and put a paper clip on that tissue. And using the tissue, you can very gently place the paper clip on the water, and it should float. So you can float metal objects, some very light metal objects on water. Okay. Now, another thing I want to talk about is viscosity. So viscosity is kind of like how much, how freely the liquid flows. So you know, honey and tar, they flow very, very slowly. So they have a very high viscosity, but like gasoline and water flow very freely. So they have a very low viscosity. And viscosity is related to like how much can the molecules flow past each other. And this depends on their shape, their size, and their intermolecular forces. So if we have strong intermolecular forces, then we will have a very viscous liquid. But if we have weak intermolecular forces, like in gasoline, then we might have a very free-flowing liquid. And probably a very important physical property that you need to know is the vapor pressure. So how fast does something evaporate, and what's the pressure of the vapor above the liquid? So we will talk about more of this later. So first, I do want to cover a little bit about phase transitions. So one important idea behind phase transitions is that, so you know, if you've ever seen like ice melting or like water boiling, so it's changing from a solid to a liquid, or changing from a liquid to a solid, or liquid to gas, or solid to gas, any number of different things. So as you might imagine, when you do this, you're changing the forces between the molecules and stuff. So all of this requires energy, or it will release energy. So, you know, like if you add ice to water, the melting action of the ice requires a lot of energy. So this melting action actually will cool down your water. For an example of like releasing energy, so you know, if you step out of the shower and you feel cold, if you step back in the shower, then all of the water vapor will condense on your skin, and so it feels warmer in the shower than outside. Okay. So how do we describe these phase changes? Well, we can use what's called not PV diagram. I'm not sure why I wrote that. So it's not pressure and volume, it's pressure and temperature. So just ignore that. I'll cross that out. So this is wrong. That's my bad. So PV diagrams appear in thermodynamics, and I don't know why I wrote that. Okay, so we have this diagram, this phase diagram. Let's call it phase diagram. So on the x-axis, we have the temperature, and here we have the pressure. So I want to talk about a few of the points here. So we have 3 different regions here. These are the 3 main regions. So we have, here is the gas area. So I'll write gas. Gas. Here we have liquid. And here we have the solid. Solid. Okay, so we have 3 different regions. So let's consider 1 atmosphere of pressure. So ordinary conditions, okay? So we start as a solid, and as we increase the temperature, we pass the freezing point. So because this is at 1 atmosphere, we call it the normal freezing point. So it becomes a liquid. So now we continue heating the liquid, and then we pass the normal boiling point. And then here we have a gas, so that it turns into a gas. Now, what happens when we increase the pressure and the temperature to some really large value? So 217 atmospheres, which is very high, and 373 Celsius. Then we pass what's called the critical point. And then you can see that the line stops at the critical point, okay? This is because past the critical temperature and the critical pressure, so gases and liquids are no longer distinguished, okay? So if you look up, in this upper region of the phase diagram, we have a phase called a supercritical fluid. So supercritical fluid. And if you look up supercritical carbon dioxide on YouTube, what you will see is as you increase the pressure, so at first you have a liquid layer and then some CO2 gas above that liquid layer. But as soon as you pass the critical point, it all homogenizes. So it turns into one phase, and you cannot tell the difference between the liquid and the gas. So it's kind of interesting. And by the way, supercritical fluid is used in to extract caffeine from coffee. So that's how they make decaf coffee. Okay. So, and here we have the triple point. So notice on these lines, we would have, if we were exactly on this line, we could have a mixture of solid and liquid. If we were on exactly this line, we would have a mixture of liquid and gas. At the triple point, all 3 phases exist at once, okay? So the triple point is used to define the Celsius scale, if I remember correctly, because it's a very exact point. And so there's an interesting video of this online. So you take a sample of liquid nitrogen, and then you lower the pressure. You start to lower the pressure. So it starts to boil. And then because it's boiling, this phase change, this boiling phase change requires energy. So the temperature of the liquid nitrogen actually will start to decrease. And at some point, it will decrease enough that you go to the triple point. So you start to get so it starts to boil and freeze and all that other stuff. It starts to boil and freeze all at once, right? So it's boiling and freezing simultaneously, right? So, and I think there's also a video of this being done with cyclohexane. So look up cyclohexane triple point if you're interested, okay? So, okay, so what is this energy change? So it's given by the symbol delta H. So we have the Greek letter delta, a capital delta. So remember before we had the lowercase delta, which is a squiggle. So now we have an uppercase delta. So delta H, and this means change in enthalpy. And we'll talk more about what enthalpy is when we talk about thermodynamics. But basically, this just tells you the change in energy. So you can think of enthalpy kind of like energy. That's not exactly correct, but it's good enough for now. So if we have a negative delta H, we have a release of energy. Why? Well, because if we have a negative change in energy, that means we're losing energy, right? So let's consider, so it's talking about the energy of some system. So the system is losing energy, right? It's losing enthalpy. So this energy has to go somewhere, you know, conservation of energy. So this means that there's an overall release of energy. Now, if the energy is increasing, if the energy of the system is increasing, so a positive delta H, we have a positive change in energy, then this energy has to come from somewhere, so we get a consumption of energy, okay? So for example, when we go to a liquid to a gas, liquid to gas, we have to increase the temperature, we have to add energy. So this means that we have a positive value of delta H, right? And for this phase transition, the liquid to gas transition, we call it vaporization. So the more exact symbol would be delta H of vaporization. So this is usually some positive value. So yeah. So let's just do one, I'll let you do one example. So let's look at the liquid to solid transition. So imagine we're taking some water and we're freezing it, okay? What do you think the value of delta H for that is going to be? So what's the delta H of freezing? Is it positive or negative? So just take a guess. Does the solid have more energy or less energy than the liquid? Less, right? Because in a solid, everything's moving slowly. So everything's tightly confined. So everything's moving very slowly compared to a liquid. So since we have less energy, what does that mean about delta H? So we are losing, we have less energy. So we're losing energy. So that means we're going from high enthalpy to low enthalpy. So, maybe it would be helpful if I actually really explicitly defined what delta H is. So I guess I'm getting of delta H equals the enthalpy of the final state minus the enthalpy of the initial state. So we have we're going from a high enthalpy to a low enthalpy, liquid to solid. So what's the sign of, so negative, right? Because we're going from, so this has a less energy, this was greater energy, so small number minus a big number is negative, right? So what about for solid to gas? What's the sign of delta H? Great, positive, because we're going from a low energy state, so the solid, and we're going to a gas. So in the gas state, everything's moving around very quickly, so we have a lot of energy. So we have big number minus small number, so positive. And by the way, if you're wondering, the explicit definition of enthalpy is enthalpy equals the internal energy plus PV, pressure times volume. So you can imagine so delta H equals the change in internal energy plus the change in pressure times volume. So, and for now, and this pressure times volume term is pretty small usually. Sometimes it's pretty small usually, so we can just ignore it. So yeah, so this is why when I say we have an increase in energy, we have an increase in enthalpy, okay? But we might learn more about that when we do thermodynamics, okay? So you don't need to worry about that for now. For now, just remember, if we have an increase in enthalpy, it's an increase in energy. So how do I clear all the annotations? Okay. So the magnitude of this delta H depends very strongly on the intermolecular forces. So this is because when we do a phase transition, we're either taking energy to break IMFs, or we're releasing energy when we form IMFs. So, for example, water with its very strong hydrogen bonds has a very large delta H, a very large positive delta H of vaporization. So we're gonna just for now we're gonna focus on vaporization. So we have a very large delta H of vaporization. But for example, maybe propane. So propane has very weak IMFs. In fact, it's actually a gas at room temperature. So it has a very small positive delta H of vaporization, but it's still positive because we're still going from liquid to gas. Okay. So to illustrate this idea, I'm gonna look at the heating curve. So so this is the temperature, and as we add more heat, so you may have done this experiment in school, in like middle school or something like that. So this is the so you can see the temperature change. Okay, so we start from ice, and as we add heat, the ice will heat up to 0 degrees, which is the freezing point. But then the temperature remains constant, actually, because at this point, we have a mixture of ice and water, right? And when we increase, when we add heat, this heat is not going into increasing the kinetic energy. This heat is going into breaking the bonds in the ice, okay? So we're breaking the bonds in the ice to form the liquid. So that's where the energy is going. So the energy is all being consumed by that. So there's no more energy left to increase the temperature. So when you go get yourself a glass of water and you add some ice to it, the temperature will always be 0 degrees, ironclad guarantee. And if you add more ice to it, you won't lower the temperature, okay? So at some point, all of your ice will melt, and now you have pure water. There's no more ice left to melt, so this heat will go into increasing the energy of the water molecules, and we see this as a rise in temperature. So we see this we have this change in temperature. And then suddenly we're at 100 degrees, okay? So now we have a mixture of water and water vapor. So water vapor is also called steam. And now we have this very big flat line because it turns out that it takes a huge amount of energy to turn water into steam. So we have to add a lot of heat. And at the same time, all of this energy is being consumed, so the temperature remains constant. So when you go to boil water, the water will always be boiling at the same temperature, and you can't just change the temperature by like adding more heat and stuff. And then eventually, all the water will be boiled off, and now we have a mixture of steam. So now the temperature will just increase, okay? What I do want you to notice is that we have different slopes. So the water line has a very low slope and the steam line has a very high slope because it takes a lot of energy to heat up water, but it takes very little energy to heat up steam because water has very high IMFs, right? It has very high intermolecular forces because we have these very strong hydrogen bonds. So when we want to move our water molecules faster, we need to kind of disrupt these hydrogen bonds, so it takes a lot of energy. Steam, we have these gas particles flying around in space. They don't interact with each other much, so we have very weak IMFs. So it doesn't take a lot of energy to get the particles moving fast. Okay? So just as we can spend maybe 10 minutes doing some of these review problems just to review the content that we covered. And these are all problems based on the AP exam. So just take a look at the questions. And if you have answers, please post them in the chat. Okay? Or you can send them privately to me. That's also fine. Okay, so I'll give you 10 minutes. I want to rank the 3 IMFs from weak to strong. Great. So London forces are the weakest in general. So this is all generally speaking. If you have a big enough molecule, your London forces will be very strong, but doesn't matter. So, and then followed by dipole, then hydrogen bonding is the strongest. Yeah. So in general. So that's a good rule of thumb. Okay. So which liquid has the highest surface tension? So you're going to want to look for the liquid with the strong IMFs. So in other words, you want hydrogen bonding. So which one of these liquids will have hydrogen bonding? The middle one, right? So yeah, so the middle one, so this one has only London forces. We don't have any dipoles and we don't have any hydrogen bonding. And although this one does have a dipole moment, we don't have any hydrogens bonded to electronegative atoms. So this one does not have hydrogen bonding. This one does have hydrogen bonding though. We have our hydrogens bonded to oxygen and we have lone pairs. So yeah, so here we have pentane. So pentane is a very thin liquid. And we have diethyl ether. So this was used as an anesthetic back in the early days of surgery and nowadays as a recreational drug, it turns out. And here we have glycerol. So glycerol is a very thick liquid and it forms one major component of fats. So especially your triglycerides. So like your animal fats and olive oil, for example. So it's very thick and it's used to like add moisture and stuff. Okay, which compound won't form any hydrogen bonds? So which one? The first one, second one, or third one? The first one, right? Great. Because all of these also have your hydrogens bonded to electronegative elements. If you look at the structure of this one, although we have hydrogen on the same molecule as fluorine, the hydrogens are all bonded to carbon. They're not bonded to fluorine. So this does not meet our criteria for hydrogen bonding. And okay, now let's look at the last one. So I forgot to number the other choices, but this is A, B, and C. So why is C30H62 solid at room temperature? So what causes this? What is responsible for its solidity? Great, London forces. So we have only carbon and hydrogen, so we don't see any real dipole because they have similar electronegativities. So of course, this molecule is very big, very huge electron clouds, so very strong London forces. And its heavy is a ridiculous answer choice, and molecules are not heavy. And the heaviness doesn't really impact how much it would attract another molecule. So when you go to take the AP test or the SAT subject test, a good strategy is to rule out the obviously wrong answer choices, and then maybe take a guess between the ones that you think might be right. Okay, now this is last one maybe. I think this appears on the AP curriculum maybe. So it's a little bit of an extra topic. So, and this definitely will appear on any chemistry competitions you take. So vapor pressure. So here we have a phase transition between a liquid and a gas. So these gas particles are all flying around, and because of this, they do exert pressure. So we call the pressure of the vapor above the liquid the vapor pressure. So makes sense, right? So vapor pressure does increase when we increase the temperature, because as we increase the temperature, more of our liquid particles move faster. So more of them will enter the gas phase. More of our liquid molecules will be fast enough to enter the gas phase. Because of this, we have an increase in vapor pressure, and this increase is, I believe, exponential. So if you look at mathematically, it should be a roughly exponential. Okay. So we do see a very drastic increase in vapor pressure. So it increases with increasing temperature, and so remember that boiling point is defined to be the temperature. So the boiling point for is going to be the temperature when the vapor pressure equals 1 atmosphere. So when the normal boiling point, so when your atmospheric conditions are 1 atmosphere, so the vapor pressure actually equals the atmospheric pressure. So the liquid can turn to gas uncontrollably. So this is the boiling point. So we have what's called the Clausius-Clapeyron equation. So the Clausius-Clapeyron equation. Don't worry about the spelling. So Clausius-Clapeyron. So the natural log of one pressure divided by another pressure equals the delta H of vaporization divided by R times 1 over the second temperature minus 1 of the first temperature. So this means that if you know the delta H of vaporization and you know the boiling point at one temperature, you can figure out the vapor pressure at any temperature. Okay, and R equals 8.314 joules per mole Kelvin. So here we have the Clausius-Clapeyron equation. So I'm going to here's one problem that uses this equation. So here we have a fun little challenge problem. So, so the relative humidity, so this is the Greek letter phi, is given by the partial pressure of water vapor. So the pressure of the water vapor divided by the theoretical vapor temperature, the vapor pressure at that temperature. So the vapor pressure we can calculate using the Clausius-Clapeyron, okay? Okay, so here is the data you need. So the absolute humidity of the rainforest is 20 grams per meter cubed of water, okay? So for every meter cubed of air in the rainforest, there will be about 20 grams of water. And the temperature is 33 degrees Celsius, so very hot. So I want you to calculate the relative humidity of the rainforest. So here is the data you need. So the normal boiling point of water, so at 1 atmosphere, is 100 degrees Celsius. To convert to kelvins, you need to add 273 to the Celsius temperature. And delta H of vaporization of water is 40,650 joules, so kilojoules. So 40,650 joules. 1 meter cubed is equal to 1,000 liters. The molar mass of water is 18 grams per mole. And we have the ideal gas law here for your convenience. And R equals 0.08206 liter atmospheres per mole Kelvin. And it also equals 8.314 joules per mole Kelvin. And one final note, these temperatures need to be in kelvins. You cannot plug Celsius temperatures into the Clausius-Clapeyron equation. So most equations in chemistry require Kelvin temperatures, okay? So I think for this one, I can give you maybe 15 minutes to solve it, I think. The pressure of water vapor from this information, and then you also need to calculate the theoretical value. And then from that, those two values, you can calculate phi. So I'll give you 15 minutes. So you can go over the problem. So I guess it might be easy for you if we just break this problem into different steps. So what are the two components for phi? Equals the pressure of H2O divided by the pressure of the vapor pressure, okay? So which I will represent like this. Therefore, we need to calculate two numbers. We need to calculate the partial pressure of water and the theoretical vapor pressure. So remember the ideal gas law? We can assume that the water vapor acts as an ideal gas, and we should rearrange this equation such that P equals nRT over V, okay? Now let's see what we can do with the information we are given. So we're given a density, a water content of 20 grams per meter cubed. The first thing we need to do is convert everything into liters because our value of R is in liters. So so to do that, we do, 1 meter cubed divided by 1,000 liters, right? This is one of our conversion ratios, if you remember dimensional analysis, equals 2 times 10 to the minus 2 grams per liter, right? Okay. Now we need to convert grams into moles because remember the ideal gas law uses moles. N is moles. So we are given the molar mass. I gave you the molar mass. So we need to multiply by 18. So 1 mole divided by 18 grams. Because again, this is one of our conversion factors. It's equal to 1, so it's allowed. So this gets us 1.11 times 10 to the minus 3 moles per liter. And then this, of course, is N over V in our equation. Okay, we're getting somewhere. So remember, P equals N over V RT. And we're given temperature. We are given temperature, and R is a constant. So this is easy to find. So it equals 1.11 times 10 to the minus 3. And I'm omitting units for clarity. Times 0.08206 times, we're given 33 degrees Celsius. And then plus 273 equals, let me figure out what that is. 33 plus 273 equals 306 Kelvin. So we're given we do the calculation, and we find that the partial pressure of water is 2.79 times 10 to the minus 2 atmospheres. Okay? Okay, so we finished now on to the relatively hard part. So we need to find the theoretical vapor pressure at 306 kelvins. So we use the Clausius-Clapeyron equation. I'm rewriting it in a way that I prefer, but it's the same thing. Can you see why it's the same? This works because ln P1 over P2 equals ln of to the minus 1 equals negative ln P2 over P1, right? So does everyone see why this equation is legit, right? Okay, so we use this equation. So we want to find P1 So we need to figure out what P1 is. And okay, we are already given a pair of pressure and temperature. We know what P2 and T2 is. So we're given a normal boiling point. So that means the vapor pressure is 1 atmosphere and temperature is 373 Kelvin. So we notice that if we plug in 1 atmosphere here, the 1 goes away. So we can simplify this to ln of P1 equals negative delta H over R times 1 over T1 minus 1 over T2, just to make our lives a little easier. So now all we need to do is plug in the T1 and T2. So T2 is 373 Kelvin and T1 is 306 Kelvin, right? So, oh, I just realized you can't see that. Okay, so you have T1 equals 306 Kelvin and T2 is 373 Kelvin. And this is divided by 1 because P2 equals 1 atmosphere. And notice how I'm neglecting units in this instance. And for technical reasons, we can omit the units here. Okay? So let's do this. And then this equals, and we're given delta H. So what was delta H again? Let me see. So 40.65 kilojoules. Okay. So equals negative 40650. Remember, R is in joules, so we need to convert to joules. We need to convert to joules. Divide by 1 over 306 minus. Let's see what this equals. Okay, so now we have that the natural log of the pressure equals negative 2.87. Therefore, pressure equals E to the negative 2.87 equals 5.67 times 10 to the minus 2 atmospheres. Okay, almost there. So psi equals pressure, H2O, divided by the vapor pressure. So this equals, so remember we already calculated it, so 2.79. Cancel out the 10 to the minus 2. So 2.79 divided by 5.67 equals 49%. Okay? Any questions? Oh.